Okay, I think we should get started. I started the recording now. So last time we talked about introduction to method limits and tensor notations. Since people are still jumping in, maybe, do you guys have questions regarding the tensor notations, introduction of method limits? Maybe this is a good time to ask a few questions you do have. Okay, maybe I should just enable this sound play. Okay, is there any questions?
I have a quick question.
Okay, go ahead.
For the fibers, how do they decide like columns would be mode 1 as opposed to rows?
How do you decide columns of mode? Oh, how do you decide column is mode 1?
Yeah, I guess, is there any like reason why they chose columns instead of rows?
I think that's
1?
just the convention.
Okay.
Yeah, that's just the convention. And I believe that if you define your own notation, basically you're calling the row as the mode 1 and the column as the mode 2. If you're writing paper about it and just consistent with notation throughout the paper, I don't think that's a problem, right? So it's just a naming, but usually by convention, people would just call column as mode 1, row as mode 2.
Okay, makes sense.
Okay, any other questions? Is there any question about the multilinear transform? That seems to be a very important concept here. And I didn't have the element-wise notation in my slides, but you can find it from my notes. Okay, is there any questions? Other questions? Okay, if not, then we can continue our discussion here. So we talked about why tensors are powerful during the last few minutes of last lecture. But most importantly, I wanted to motivate why we're talking about uniqueness, right? So, we're talking about not unique without eigenvalue gap in matrix orthogonal decomposition. So I think there are two things. So one thing is, yeah, so is there a way that I can write here? I don't think so. Can I write? Oh, I can. So most important thing is, can you see my writing?
Yeah, we saw a 1 in the corner.
Okay, wonderful. So the most important thing is, why we care about decomposition. And then the second most important thing is why we care about uniqueness of decomposition. Oh, okay, so these are the most important questions before we understand this slide. So the first question, why do we care about decomposition, really comes back to our moment matching, right? So if you remember that, let me go back to that again. If you remember that, right? So this moment matching for first order moment is gonna be a matching a vector equal to another vector, right? Because if it is a first order moment, then the x is a vector. Expectation of x is also a vector, which is represented as a function of theta, right? The model parameter. And the right-hand side is gonna be like a value, right? Sorry, a vector with some kind of value that you estimated from the examples in the training data set, right? So that's gonna be a vector. And now if it is a second order moment, it's gonna be a matrix. And that matrix will be something related to some kind of factorized form, which is a function of the theta here. And then the right-hand side is gonna be just a matrix evaluated from your input examples again, right? So if you think about this, essentially doing this moment matching would oftentimes reduces to doing decompositions of this matrix for a third order moment, or a tensor, a third order tensor for a third order moment matching. So that's the reason why we care about decompositions. Although I haven't given you a concrete example why we need decomposition, but I'll show that soon today. Okay, so that's the first reason. Then the second reason is this kind of uniqueness. Oh, so sorry, the second question we ask is this uniqueness. Why do we care about the uniqueness of the decomposition, right? So the reason why we care about the uniqueness is through these decompositions, we will recover the model parameters, right? So if we are not able to recover a unique model parameter, then this decomposition is useless, right? Because we cannot get, we cannot uniquely recover the model parameters, right? They're not identifiable. That's a problem. And that's why we need to make sure that the decomposition actually gives you a unique solution and therefore a unique recovery of the model parameters, right? Because we care about the guarantees. We care about recovering the model parameters with guarantees. So I hope this is a, clear explanation of why we care about decomposition and uniqueness of decomposition. So now going again, we talked about matrix orthogonal decomposition is not necessarily unique if you don't have eigenvalue gap. And this example is showing you that, right? So if you have like this E1 here and E2 here, they are, E1 and E2 are orthogonal bases, and those happen to be the eigen vectors of this unique, of this identity matrix, but they are not unique. Any rotation of these E1, E2 could be an eigenvector. It could be the set of eigenvectors for this identity matrix. So that's a problem, right? So if you happen to have some kind of matrix that's, this empirical estimation of the moments, that's a matrix, and you do a decomposition. You're hoping that this result of the decomposition will give you the model parameters, but now you can't, right? So now that's why we're saying tensors are more powerful. The reason is that without eigenvalue gap, tensor orthogonal decomposition is still unique, unlike matrix orthogonal decomposition. And here is the reason. Okay, so let's assume that we have a tensor. So I have a picture here, but let me give you a more concrete description using math. Can I write down here? So if I have a tensor, I cannot write it here. So if I have a tensor, okay, so this tensor can be written as, so U1, tensor U1, tensor U1, plus U2, tensor U2, tensor U2. So if this is my underlying tensor, of course, I only get to observe this third order object. I don't get to observe these U1s or U2s, right? So, but I know this is my ground truth. Of course, my goal is to recover them. So now is that, so you can see, we're assuming that U1 is orthogonal to U2. So this is a tensor orthogonal, like tensor with orthogonal components, U1 and U2, right? The rank is 2, apparently, right? Because you can write it in terms of these two rank 1 tensors, and each rank 1 tensor is just a outer product of a few vectors in 3 vectors here. And now the the singular values here are just 1, right? Because you can see here, there is no, the coefficient are just 1 here. So in that sense, there is no eigenvalue gap because both components have a eigenvalue 1. Okay, so now, I hope this is clear. Oh, can you rotate the iPad? Oh, is this better? Is this better? I just rotated it. Okay. All right. Sorry about that. Okay. So now what I'm saying here is that the slice of tensor has eigenvalue gap. So let's see, what does the slice mean? Remember, our tensor is this form, right? Let me use the simplified notation here. So our tensor has this form. So one slice of the tensor could be actually written as, if you take one slice, let's say slice I, then it would actually be equivalent as so it's like U1 I. So the ith element of the U1. So this is going to be a scalar, and then multiplied with this matrix, and then plus U2I, and then multiplied with this matrix. Okay, so this is nothing but, thinking about the definition of the slice. If you think about it, you will see why. Just, I'll let you think a little bit about it, why this is true. Of course, when you are slicing a tensor, if you don't know the U1s or U2s, you wouldn't know how to slice using this equation, right? But what you would do is just taking the slice, literally taking the slice of the tensor. But because I know the ground truth U1 or U2, I can write in this form. They were equivalent. So you can take a moment to think about why they're equivalent. Think about the tensor product, right? How do you get the tensor product? What's the notation? What does each element mean in this tensor product, right? So the ijk element in a tensor product just means the ith element, of the vector along the mode 1, jth element of the vector along mode 2, and the kth element along the mode 3. Right? So that's why essentially taking a slice of the tensor becomes something like this. Any questions? Is there any question why this is true? Okay, so if that's fine, then you can see, so as we claimed here, right? So if you're looking at every slice of the tensor, so it's gonna be a matrix. And with very high probability, these two quantities won't be the same. These two, here, these two quantities won't be the same, right? Unless U1 and U2 are equal to each other everywhere. Can you see? Do you agree? Why this, they might be equal in some elements, but it is unlikely that they will be equal everywhere for every I, right? Sorry, U1I and U2I shouldn't be equal for every I, right? they shouldn't be equal for every eye. Maybe they are equal for some eyes, but they shouldn't be equal for every eye. Otherwise, they won't be orthogonal to each other, right? Okay, I hope this is clear because, you know, I hope, I don't know, I know this is hard to get, you know, any feedback because we're doing things online, but if you could, you know, signal your thumbs up or something, I can then be more confident to proceed.
So this is saying at least some slices of the tensor have eigenvalue gap?
Exactly.
Okay, makes sense.
Exactly.
Thanks.
Yeah, so assuming at least there's one that should have eigenvalue gap, right? Otherwise, you know, U1 would not be orthogonal to U2. So if that's the scenario, then, you know, you might argue, which one do I choose, right? I don't know which one to choose. So the answer is you could try to do a linear combination of these slices, right? So like what I'm writing here. So this CI is some kind of coefficient. You do linear combination. You're just doing a linear combination of all the slices of the tensor. And then essentially, you can see, you know, you are just, in terms of the coefficients, you're just doing a linear combination of this U1 along all its coordinates and the same linear combination of U2 along all its coordinates. So with high probability, they won't be equal. Okay, so basically, unless your coefficient is chosen in a very, you know, in a very extreme way, that you're very unlucky that under this coefficient, it happens that your, you know, linear combination of U1 elements and linear combination of U2 elements are the same, but with high probability, that won't be true. So essentially, you find, you know, a way to create an eigenvalue gap, which is doing a linear combination of the slices of a tensor, and then, you know, do a orthogonal matrix decomposition on it, on this linear combined slice. You know, that would become a matrix, right? You were just doing that on that matrix. So with high probability, you will get a unique answer, and you will uniquely recover U1 and U2. Okay, as I said here, if you do have eigenvalue gap, matrix orthogonal decomposition is unique. You can uniquely identify these vectors. Okay, so is that clear? I mean, the details is clear, but I haven't got to like interpretation of the results yet. So we see this difference, right? We see this, of course, Michael asked me last time, you know, when I say why are tensors powerful, I'm using matrix as, you know, a counterexample and to show like, you know, why matrix is not as powerful as tensor. So here I wanted to clarify that by tensor, I mean order 3 or, you know, above. So it's a little bit different from the wide notion of tensor. So I'm specifically referring to tensors with order 3 or higher. So here, tensors with order 3 or higher orthogonal decomposition will be unique without eigenvalue gap. And this is different from a matrix orthogonal decomposition. That's why I say tensors are powerful. Why? Because they have this extra dimension that would give you more information about the data structure, right? Whereas matrix is like the structure really lies in a 2-dimensional object. So tensor with this high dimensional object with this extra information would give you more information for you to uniquely identify the structure within the tensor. And that's why sometimes, you know, when you're doing moment matching, you could be failed by doing a second order moment matching, but a higher order moment matching would be successful. Okay, so I hope this is clear. And now I will give a concrete example of using tensor decomposition and using method moments to solve a latent variable model. And this is going to be the first latent variable model learning we learn in this class, right? So it will have theoretical guarantees, which is very nice. And that's the reason why we're learning about them. But the difficulty here, or I guess the caveat here is that it is oftentimes very tricky to come up with the right term to do decomposition on. So I'll make that clear later. Okay, so here we'll be focusing on single topic model, single topic documents, and we're using topic model for them. So can you tell me, maybe you can tell me if you are familiar with topic model, or if you've heard about topic modeling. Can you do a thumbs up if you've heard about topic modeling before? Okay, I think not a lot of us have heard about that, but that's fine. So here is a general topic modeling. Usually people use so-called latent directional allocation to denote, as a very widely used model for topic modeling, just like a mixture of Gaussian, right? So, if you have dots that looks very like clustered and they're kind of like, concentrated at the center, then you might want to use a mixture of Gaussian to model the data. Here, it's just like for text data that you observe counts of the words, it is very likely, and people have shown that using a latent directional allocation, which is just another latent variable model, just like mixture of Gaussian, people have shown that using latent directional allocation is very helpful for modeling these kind of, document data or text data when you're only care about the counts of the vector. So it's called the bag of words, right? So you don't care about the order of the words, you only care about the counts of the words, right? So this is a simplification that we are using here. So the general topic model, here is an example. So let's say, so this is so-called the generative model, like the generative process of how data is generated from an underlying model. So here is the generative process. You have K topics, in this case is 4, K is 4. So you have K topics, each associated with a distribution over vocabulary words. So for example, in the sports, right? So all these, each of these columns is corresponding to a word in your dictionary. And, the amplitude of, or the height of these columns are just showing the probability of choosing that word under the topic sports. Okay, so let's say this word is football. Then this is the probability of choosing football under the topic sports. Is this clear? And then, let's say this word is basketball. Then this is the probability of choosing the word basketball when under topic sports. Similarly, here's science. And let's say if, this is the foot. So of course, these are corresponding to the same dictionary. If this is football, then this will also be football. You can see my cursor, right? I am.
No.
Yeah, I'm using my cursor. So let's say this is the football, then this is also the football. If this is basketball, this should be also.
I don't think we can see it though, the cursor.
Oh, you cannot see my cursor? Oh, sorry. This technical difficulty is. Okay, how should I? How should I do this? Yeah, okay. You can see what I'm writing. So let's say this is the word football. Okay, and let's say this is the word basketball. So all I'm saying is the order of the words in your dictionary should be the same. right? So if this is football, this should also be football. This is basketball, this should also be basketball. That's what I'm saying. Okay, is this clear? Okay, so you know, each of these are just a conditional distribution. So it's like the distribution over vocabulary words conditioned on this topic H from 1 to K. Okay, so you have that for all the topics. So that's, we call it K topics. So now, you know, once we have that, there is this more important quantity called a hidden topic proportion. So people often ignore that. And this is very important. This is saying that, you know, for a, specifically for a document, you know, because we are looking at, you know, like a single, if you're looking at a, if you're looking at a single topic model, then you would only talk one topic in a document. But here we're assuming that you can talk about a mixture of topics. So that's why the omega I here just denotes the topic proportion for your document I. It is gonna be a simplex, meaning like, you know, it's a probability vector. Okay, and this simplex just showing what is the proportion of the words that are talking about sports versus science versus politics versus business. Okay, so is this clear? This is just the topic proportion for each document. But of course, you know, if you have a single topic model, then this will be just one of them. So it's gonna be a one hot encoding, but here it is just a probability vector. You can call it a mixing vector, okay? So now with this model parameters, you can see this is very much like a mixture of Gaussian, but the difference is there, mixture of Gaussian for each topic, it would be characterized by the conditional mean and the conditional covariance, whereas here, I only need a conditional distribution over vocab words, right? You know, what's similar with mixture of Gaussian is that we all have a mixing weight, and this mixing weight should be characterized by this omega I taken average over all documents. Okay, so similarly for each dot in a mix of Gaussian, you know, it can only be colored red or, you know, green or black, right? So it's like one dot can come from one cluster only. But the difference here is that in topic modeling, each document could come from different topics, right? It could talk about sports as well as politics. Okay, so now with that topic, you know, with the description of the model parameter, we're ready to see how does the generation process go, right? So you first would sample, you know, omega I from a mixing distribution. So for each document, you would sample from omega I. Okay. So once you have omega I, let's say in this document, you happen to have 0.6 for sports, 0.3 for science, 0.1 for politics, and no business. Okay, so you know 60% of the words are sports, 30% of the words are science, and 10% are politics. So now what is this showing here? This is showing the word count per document. Okay, so sorry, this thing is blocking the view. Yeah, so this is the word count per document. This word count per document essentially is just like a, you know, without thinking about the order of the words, you're just looking at the number of times it occurred for each word. And the order is the same as the dictionary order that you used in these model parameters for these K topics. Okay, so you can see that this bag of words are generated from this mixture model with this mixing weights and the K topics. Okay. So for instance, for the sports, the topic for the sports essentially is the vocabulary distribution of vocabulary words. For example, the first element is just the probability of play, conditional sports, and the second element is the probability of game, conditional sports, and so on. So each of these will be a vector, right, characterizing the distribution over vocab words. And now if you just stack them together into a matrix, so here, if you're stacking them together into a matrix, then you can see this is just so-called the topic word matrix, because each column is the conditional probability of these vocab words distribution. Okay, so I think this is clear. Now this slide is slightly, a slight change of the previous slide. You can see now this becomes a single topic documents. So that means these omega i's are no longer probability vectors, but just von Hardt encodings. If it is E1, then this only talks about sports in this document. If it's EK, only talks about business in this document, right? So when you're joining the back of words, the generating process only would concern the conditional distribution that you are talking the topic in this document, right? So all the others won't be helpful because you only talk about sports in this document. However, in the next document, you might be talking about science, right? But that means that overall, the proportion of, the percentage of talking about sports and percentage of talking about science is still there, right? So you still, it's not like, all your documents in your corpus is only talking about sports, right? So, 20% of the documents talk about sports and 80% talking about science. That's fine too. But what I mean here is that for each document, there's only one topic within this document. Okay. All right, so to recap, what are the model parameters for topic model for single topic documents? We wanted to use the single topic documents for simplicity here. So what is the topic model? What is the model parameter? First is the topic proportion, right? So it's the percentage of documents talking about each topic, right? So that's the topic proportion. So then the next thing is the topic word matrix, which, like I said, is the stack of the conditional probabilities for each topic. Okay, so let's say if you have a topic word matrix A, A1 through AK are just the conditional probabilities, and the AJH is just the probability of word equals to EJ, condition on topic equals to H. Okay, so those are the model parameters, just like in your mixture of Gaussian, these are the model parameters. So what's the goal? Going back to the goal, right? The goal is to estimate the model parameters AH and WH given IID examples of N documents. Right? So how are the documents are given? They were given through word counts. Right, so I from 1 to N, you have the CI is just the word counts. So it's a vector of length vocabulary. So if you have 10,000 words in your dictionary, then this word count is going to be a vector of 10,000 length. Each element is the number of times that word occurred in that document. Okay, so that's called the word count. So if you divide it by the length of the document, you will get a frequency vector, which is xi, denoted as ci divided by L. L is just the length of the document. And as you can imagine, the length of the document is the summation of the word counts in each coordinate. Right? So is there any questions? Okay, hopefully this is clear. Well, so as I said, right, so doing like learning latent variable models are actually is essentially NP hard, but we have to make some mild assumptions. So when I was saying this, I was talking about learning mixture of Gaussians. I said, people are making this separability assumption and all the other assumptions, but in our tutorial, we will be focusing on this so-called non-degenerate assumption. So basically, it's a linear independence between the conditional means of these Gaussians. So now going back to our topic model, it is also a similar assumption. We're assuming that these topic word matrices have linearly independent columns. So what does that mean? It just means that these conditional probabilities, so each column of these are just linearly independent. So it's basically saying that, let's say you have a conditional probability for topic music, okay? And the topic music shouldn't be a scaling of topic sports, right? So if that's the case, then music and sports are really just the same, right? If there are just linear combinations, or more, maybe you might be saying that's a too simplified example. So maybe my politics is just a linear combination of sports and science, and that's also not allowed, right? If your politics is just a linear combination of sports and science, why do I have a new topic called politics? Why don't I just, divide 30% of my politics topics as sports and 70% as science, right? So it doesn't make a lot of sense to define a new topic if this topic is just a linear combination of other existing topics. So that's why we make this assumption called non-degenerate model, meaning like the columns of these topic word matrices are just linearly independent. So does each document have the same mixing vector? Oh, no, we don't, right? We don't assume that each document have the same mixing vector. Actually, I wanted to clarify. I think we might have a confusion here. So for the most general topic model, each document would have a WI here, and is a topic word, is a probability vector. So let's say if this document 1 has like 0.1, 0.8, 0.1, and 0, then it just means 80% in this talk, 80% of the words in the document talk about science, and 10%, as well as 10%, 10% talking about sports and 10% talking about politics. So that's for this specific document. But for another document, you could have a different mixing, you could have a different topic proportion for this document, maybe 0, 0, 0, 1. So it just means this entire topic, this entire document is talking about business. Okay, so they could be different. But what I wanted to emphasize here is that in today's lecture, we won't be talking about the general case of omega I being a probability vector. We only consider they being one-hot encoding. So the document can only talk about one topic. So that's called a single topic document. So we're only considering that scenario. I wanted to make sure that's clarified. Yeah, so also, if I don't have the superscript, when I talk about omega here, then this is across the entire corpus. Okay, so it's not for a specific document. Right, so think about the mixing weight in mixture of Gaussian. Your mixing weight doesn't refer to any specific data point, right? Because the specific data point can only belong to one of these clusters. So essentially, in that sense, the single topic model kind of correspondence, right? So but however, if you're looking at the every points in expectation, some percentage of them belong to cluster A, some other percentage belong to cluster B. So that's something that might be a little bit confusing. Okay, so now going back to our non-degenerate model, we're making the assumption of linearly independent topic word matrix columns. So the generated process, again, is just you choose an H from a categorical distribution distributed using this omega 1 through omega k. So you choose H. So this now H is just a topic, sports, politics, business, or other things, right? So you're choosing just one of them. So this is denoted as H. H is just one hidden topic. Now, once you choose that, you would generate L words in this document. Every document is generated independently according to A sub H. So notice that A sub H, the subscript here H just denotes the corresponding topic distribution, right? So A sub H is the corresponding topic distribution corresponding to topic H. Okay, so you only look at that specific probability. But then you're doing that for L times because you're generating each word independently in your document. So once you do that, you can verify that the expectation of X is gonna be the summation of the probability of topic equals to H, which is essentially the omega H, and the expectation of X conditioned on topic equals to H, which is just the AH. So this is saying that expectation of X is summing over omega H, AH. Notice that omega H is a scalar and AH is a vector. Okay, so is there any confusion about this, or is there any questions about this equation here? Okay, so another important thing to notice is this, expectation of X condition on topic equals to H is essentially written in this way. So I wanted to emphasize that what is this? This is actually, let's say dimensionality is D. So this is D. Is a length D vector, right? D is the vocabulary size, let's say. So, it is a vector. So this is I think people need to understand this. And it's not easy to understand. It's kind of tricky here. So this is a vector. And essentially, what is this vector? So this is a basis vector. This basis vector is talking about, each element in this vector. Okay. So, if this is EI, then this quantity is just for this EJ, sorry. Right? Because a vector can be written as the summation of this vector from each coordinates, right? So what I'm really saying here is that if you have a vector, right, with all these elements, it can be written as this thing plus and so on, right? It can be written as the summation of the coordinates for them. So you can see, so that's why I say EJ. So this is E1, E2, E3, and so on. But you have a scaling factor for these basis vectors. And these scaling factors are essentially the probability of word equals to EJ, conditioned on topic equals to H. So these are the scaling factors. Okay. So this is very important to note. And now, because of that, you're just denoting it as AH. So basically AH is a collection of these probabilities for each coordinates, right? So AH is still a vector. Okay, so let me erase this. Okay, so now with that, I wanted to introduce first M1. So as I said, for vector moments, you're mostly matching moments. So we can start with the simplest one, which is the first order moment. So M1, you can also think of it as the distribution of words, or M1 hat, which is the occurrence frequency of words. So M1 is the expectation of X. It can be written as the summation of omega HAH, as we said before, right? So M1 hat is nothing but the summation of these observations, right? Of these data, of these training examples. So it's 1 over M summing over X superscript I denoting the I's document. And each of these XI's are essentially just the frequency vectors, right? For each document. So as you can see, I can get my MI here. So let's just, this is my MI, it's gonna be a vector. And now, because this is my MI hat. Now my MI can be thought of as like the right-hand side of this equation. So, basically the linear combination of these columns, of these probability vectors. So as you know, right, you observe this, right? And you wanted to solve this. You wanted to find a solution for each of these components. So what does this mean? It means that you are trying to do a vector decomposition. And this essentially is the reason why I was talking about decomposition before, right? You observe the M1 hat, right? And by moment matching, you wanted to make sure that M1 hat is very close to M1, right? The M1 is a linear combination of these things, right? So, if you're solving this is essentially using a vector decomposition, right? If you're able to decompose your M1 hat into these vectors, linear combination, then you are done. You are learning all the model parameters, right? But what's the problem here? Are you able to do the vector decomposition? Are you? That's very obvious that you cannot, right? You cannot find a unique decomposition of a vector. Essentially, you can just, swap the elements between these components and would give you the same M1 hat, right? So therefore, for example, you can swap these, or you can, swap these things, right? You can do a swapping of all the, of all the topic words, the columns of the topic word matrix, or this conditional probabilities, and you can still get the same M1 hat. So is there a question? Or is this clear? Am I confusing people? Okay. All right, so.
I have a question.
Yes.
So here non-degenerate means that each document can belong to only one topic, or it can be a mixture of topics?
No, so that's not the non-degenerate. I mean, each document can be one topic. It's just like a single topic model. You know, it's just a special case of a general topic model. But the non-degeneracy just means the topic word matrix have linearly independent columns.
Intuitively, what does that mean? How?
So first of all, what's the topic word matrix? Each column of the topic word matrix is just a conditional probability of generating words conditioned on topics.
Right. Yeah.
Right. So, you know, you have sports, science, politics, and business. Each would have a different way of generating words, right? And essentially a different distribution of generating words. This is just saying, you know, my topics cannot be a linear combination of sports, science, or business.
Okay.
Right. So that just means that so let's use a very simple case, right? Let's say we have 4 words in your documents. Let's say we have 4 words in your corpus. So sport, let me use football. And science, we would use, I don't know, machine learning. And then politics, let's say election, or I don't know, what is a typical word for politics? I don't know, I'll just use election, but this might be wrong. But anyway, so business, I'll just say 401k, okay? So I only have these 4 words in my entire vocabulary. This is like a very extremely simplified case. So, you know, what is the probability, conditional probability for sports? So for sports, I would just say this conditional probability is just 1, 0, 0, 0. This is my conditional probability for sports. And for my science, I would just say 0, 1, 0, 0. This is my conditional probability, okay? And do you see where I'm going, right? So I'll just have like a politics, which is like, you know, 0, 0, 1, 0. I don't have space there, but business is just 0, 0, 0, 1, right? So I have all these conditional probabilities, and this is a very extreme case that I'm showing here. Like, you know, these conditional probabilities are just like one-hot encodings, but they are still a probability vector, right? So what I'm saying is, like, you know, this business shouldn't be a linear combination of sports or science vector. So do you see what I'm going? I'm just saying that how you are generating the words shouldn't be a linear combination of, so how you are generating words in business shouldn't be a linear combination of how you generate words in sports and how you generate words in science.
Okay, so basically
a linear combination, then this just means that you're living in the same space of sports and science. Why do you create a new topic?
Yeah. Got it. Yeah.
Right.
Yeah.
Okay.
Thank you.
So now, you know, this is the assumption we're making. Of course, you know, our model will be able to uniquely recover the model parameters under this assumption of non-degeneracy. But now, you know, I'm just talking about the M1 moment matching, you know, so setting M1 to be M1 hat, right? You can see because, you know, there is no unique decomposition of vectors, so therefore you cannot uniquely identify model parameters just using moment 1. Okay, moment 1 is essentially a occurrence frequency of words. Does that make sense? Okay, so that's why we need to make, you know, a more sophisticated design of the F when we're talking about the topic word, the moment matching. So now let's say it's a second order moment. So M2 is the distribution of word pairs, and M2 hat is the co-occurrence of word pairs. So first I wanted to ask you, do people agree that M2 can be written as a function of the model parameter this way? So M2 is just summation of omega h AH tensor AH. Is this clear? How do we derive this? Right, so we know that M2 equals to expectation of XX, right? X tensor X, right? That's no question. But why can it be written this way? So first of all, do people agree with this Taoist rule of the conditional expectation?
Yes.
Okay, so if that's the case, then I'm just writing this as do you agree? This is nothing but the definition of expectation of this thing over H, right? So I'm just summing over, let me write it more clearly. Just summing over all possible values of H because H is now categorical. I'm summing over all possible values of H, but for each value of H, what is the probability of taking that value is omega H. And what is the function value for that? It's just the expectation of X, tensor X conditional H, right? So now with that, we'll see. So expectation of X, tensor X, because you have conditional independence. So actually this becomes you'll get that. And as we said here, this expectation of X is nothing. Expectation of X conditioned on topic H is just AH. So therefore it becomes, okay. So it's very important to notice that, this is written in this way, right? It's like the probability of the conditional probability multiplied with the basis and summing over all the bases. Okay, so you can now write it in terms of the M2. So you can see the right hand side of this equation here. So this is just, A1 tensor A1. This is A2 tensor A2, A3 tensor A3, and so on, right? And then the coefficient for each of these are just W1, W2, W3, and so on. Okay, so this M2 hat here is just this matrix, right? So you're doing moment matching. You're setting this M2 hat to be this thing. So of course, A1, A2, A3 are all unknown. So what is this? It's nothing but a matrix decomposition. And that's why we talked about doing decomposition here. Okay, so now the problem really, the takeaway message is really like for moment matching for latent variable models really reduces to do decompositions of tensors of every order, right? From 1 to anything that you choose. Right, so you can see this is essentially doing decomposition of the M2 hat, which is a matrix. And you hope to recover this A sub H for all H from 1 to K. Okay. I mean, this lecture, I don't know why it's like much slower than I hoped. Maybe it's just because I couldn't see any feedback. So the problem now is like, whether matrix decomposition is unique, right? With this M, when you do decomposition of M2 hat, can you get a unique recovery of the model parameters? So the answer is no. Actually, matrix decomposition only recover the subspace, not actual model. Why? So when you think about the matrix orthogonal decomposition, even the matrix orthogonal decomposition will require that the components have eigenvalue gap to be unique, right? But here there is not. This is actually not a matrix orthogonal decomposition because your components are not orthogonal, right? They are just linearly independent. Right? So linear independent is different from orthogonal. So if you have only linearly independent components, you cannot have a unique matrix decomposition. So actually, if you can do some kind of rotations for your, let's say, eigenvectors of this matrix, you would still get these, any of the rotations of the eigenvectors could be a candidate of your model parameter. So you don't have a unique recovery. So what you actually do is that you can find a W. So this W is going to, so W transpose A1 will be like V1. And W transpose, sorry, this is W. W A2, it's gonna be V2. So this is corresponding to A1. This is corresponding to A2. This is V1, V2, and similarly. Okay. So then, you can find such a W, although this A1, A2, A3 are only linear independent, but you can find a W under such, a linear transform. Your V1 and V2 and V3 are actually orthogonal to each other. So you can do that. You can find such a W. Actually, you can find many such Ws, but you only need to find one of them. And you remember the W you use to do this transformation. So once you find that, you will find these V's that are orthogonal. And essentially, what you can do is you can now go to the higher order moment. So now this is a third order moment. So it's just a co-occurrence of word triples. And essentially, you're looking at the distribution of word triples. And specifically, you're looking at expectation of X, tensor X, tensor X. So this M3 can be written similarly as what we said before for the matrix case. This tensor case, you can also write it in this form. So it's gonna be summation over H, omega H, the mixing weight multiplied with this outer product of the conditional probabilities. Okay, and you do that for 3 times. So this will be like the right-hand side here. And now this M3, which is just a empirical estimation of the co-occurrence of word triples, is this form. And this will become a tensor here. Okay, so this tensor, as you know, by doing moment matching, this M3 hat is equal to this M3, right? And then the right-hand side is just the M3. So, so then you might say, oh, can I do a tensor decomposition to recover the model parameter? The answer is yes, possibly, but we don't know how to do a tensor decomposition with linearly independent components. We only know how to do tensor decomposition with orthogonal components. So can we make the tensor orthogonal to have orthogonal components? So remember before we said, when we have this matrix, right, we can find an W that makes the components to be orthogonal. So now, can we do that on this tensor to make sure that the components are orthogonal? The answer is yes. So you can do this through this multilinear operation. So we learned about this multilinear operation. So remember, what is the definition of the multilinear operation? So if you have a tensor M3, you do the multilinear operation using your matrix W. So this W is the one that is orthogonalizing your component, right? This thing, right? And V1 is orthogonal to V2 and orthogonal to V3. Right, so you can find this W and you just do this multilinear operation on the M3. Now, you can see because of the definition, so you actually have the components that are orthogonal to each other, right? So W transpose AH are now orthogonal to each other because of this multilinear operation, right? Because you find your omega, you find your W that way to have this orthogonality. Okay, so now again, if you are, so this is saying that I can have this M3 W here on my right hand side. So on my left hand side, I can also have my M3 hat of my W here, right? I can also do that, and that is also easy to do. All I'm doing is whenever I have a new data coming in, I could just do a linear transformation of that data to get a new vector, right? Maybe this is just my x tilde I, right? This x tilde I is some kind of new vector after this linear transformation. And then I can do similar things to calculate the co-occurrence of word triples of this x tilde thing, right? So that, what does this mean? This means that we actually reduced like a moment matching for third order moment to be a orthogonal tensor decomposition problem, right? So you have this tensor on the left-hand side. You do an orthogonal tensor decomposition, you would get the orthogonal components here, right? And then these orthogonal components are going to be unique because we know that orthogonal tensor decomposition is unique, as we said when we were saying, why tensors are powerful. We showed that it's unique. So we can uniquely identify V1, V2, and V3. And similarly, since we know the W here, therefore we can uniquely identify A1, A2, as well as A3. Okay. So that completes the picture, right? So we basically, through using the first three order moments, we derived a matrix and tensor decomposition method. We call it spectral method to identify model parameters. And that model parameter can be identified with guarantees, right? Because we know that this will exactly be the model parameters if you observe enough samples. So is there any question? Right, so in the end, you would get the model parameter estimation AH hat by doing the inverse problem, right? So you would get your VH hat and then multiply with the pseudo inverse of the W transpose. Is this clear, or do we have questions so far? Right, so here comes the identifiability, right? So like how long must the documents be? Meaning like, basically we said for identifiability, we need to look at the co-occurrence of word triples. But if your document is even shorter than 3 words, then we cannot find the co-occurrence of word triples, right? We don't even have 3 words. So basically it means that the documents have to be of length greater than 3 for our method to work, right? Of course, for this concentration bounds to hold, remember when we're doing moment matching, we're doing like an approximate equality, right? So this approximate equality is more accurate as we have more examples observed in our empirical estimation of these M hats. So in order for like concentration bounds to hold, we hope to observe as many documents as possible, right? So that's where we can get the more accurate aggregated statistics and then do moment matching. But in terms of the document length, we want it to be at least greater than 3 in order for us to actually get the co-occurrence of word triples. Right? If it is smaller than 3, then we cannot find co-occurrence of word triples. We maybe find pairs or just the occurrence of words, but those are not useful for the identifiability of the model. Another very important thing I wanted to say is that we're assuming the data is in high dimensional space. If the data is in a one-dimensional space, like your number of attributes in your data is just 1, then all of this won't work, right? You won't even have a tensor, right? Because your tensor would be 1 by 1 by 1, which is essentially 1, right? So this would only work if you have high dimensional data or like multi-dimensional data. Is there any question? So if not, then I think, so the takeaway message is that consider topic models satisfying linear independent word distributions under different topics. So the parameters of the topic model for single topic documents can be efficiently recovered from distribution of 3 words documents. So this, basically the word triples. You look at M3, which is the third order moment of a single topic model. Then it can be written as a tensor, right? So M3, and the tensor actually have components that are corresponding to the model parameter, right? A sub h are the model parameters for all h, right? Omega h's also are the model parameters. Those are the mixing weights, right? So you can see that you can find a correspondence between the M3 and the model parameters, right? And you could also have an estimation of the M3 hat, which are the co-occurrence of word triples. So if you do moment matching, you can just do a tensor decomposition to find the components, right? The caveat here, or the subtleties here, is that you don't do a direct tensor decomposition on M3, which is D by D by D, right? Which is huge. You actually do some kind of transformation to get an actually smaller tensor using this W matrix. We call that whitening matrix, right? Then you transfer the tensor into an orthogonal tensor. And this orthogonal tensor is actually much smaller, okay? You find the W using like a matrix decomposition on the second order moments, you find the W, and you do a multilinear operation on the gigantic tensor to find a smaller tensor. Then you do a decomposition on the smaller tensor. And the result would give you, the result would essentially lead you to your parameters, WH and AH. And more importantly, 2-word documents are not sufficient for identifiability. We have to have documents that are longer than 3 words. Okay, so I don't want to show the results here. You guys can take a look later on. This is just showing like how tensor methods compared with variational inference could be much more accurate as well as more efficient. Okay, so the variational inference is the traditional way of solving latent Dirichlet allocation, or the learning of these latent variable models. So this tensor decomposition way or the moment matching way is could be much more accurate as well as more efficient. So I wanted to say next time, so next lecture, we will be talking about a few algorithms for tensor decomposition, because now we've learned how to use moment matching to solve for latent variable model. Now everything reduces to doing a tensor decomposition, which we don't know how to do yet. So I'll be focusing on that. And then, so if we have time, I wanted to talk about some kind of methods like tensor representation incorporated into neural network and how that would help in terms of making the neural network more expressive as well as generalize better. So that's gonna be our Thursday lecture. So thanks everyone.